Is there a shuttle service? Please.
Yeah, we're just.
There's shuttle service. Cross off this little like. You know what I'm talking about? I do it. Over drop off like. What if I'm gonna jump in? Like right now.
Let's go to page 13. So I said that we're going to have a much more efficient way of finding derivative. No longer are we going to have to use the limit definition to get to the derivative, even though that was a good place to begin the process because we need to see that there was a definite connection between derivative and slope. But now we have a much more efficient way called power rule that can allow us to get to our derivative much quicker in just one step rather than have to go through, a series of direct substitution and evaluating limits. Now, we're going to keep saying the word slope over and over again because I think that is a nice tangible way of connecting this word with something that doesn't feel so abstract, right? You see, here word derivative just sounds like an abstract concept, but it's just slope. So let's say a function is at y equals 5. So f of x equals 5. Think about what that graph looks like. Just a horizontal line. What is the slope of that horizontal line? 0. So that's why this is the constant rule saying that anytime I have a constant, think of that constant as just that some horizontal line. And then any horizontal line's derivative or slope is always 0. So the derivative of a constant is always 0 because the slope of a horizontal line is always 0. Right. So here's power rule. Power rule says if I have a variable raised to an exponential, rational value, like raised to like a 1/2 or raised to a 2 or raised to a 3, the derivative is simply this. I'm going to bring the exponent down in front, make it into a multiplication problem, and then subtract 1 from the exponent. So we're going to bring the exponent down as a coefficient in front of the variable, and then we're going to subtract 1 from the original exponent value. So for instance, if I had a f of x equals 5x cubed, then my derivative, rather than going through a whole limit definition process, we can just quickly do this. Bring the exponent down. So what is that 3 going to do? Multiplication. So it turns into what? 15. And then we subtract 1 from the exponent. So 3 becomes 2. And so now we quickly are able to create a slope formula that will describe the slope behavior of this original graph. So power rule we're going to learn more derivative rules down the road, but power rule is going to be the rule that we're going to use. We're going to see more often than anything else. You're going to use this. You're going to be more familiar with this rule than anything else because we're going to see it, every time we do derivatives, pretty much. Having said that, we do have quite a few conditions that need to be in place before we can do power rule. Okay. So the first is if you see radicals converted to rational exponents, it's easier to know what to bring down and subtract 1 from if we have that as a numeric value. So for instance, if you see square root of x to the 5th, you want to rewrite it as x to the 5/2. Next up, power rule only works if the variable is in the numerator. If your variable is in the denominator, we have to bring it up first because this power rule is designed for the numerator only. It's not designed if that variable is in the denominator. So for instance, if I had 1 over x cubed, I first have to rewrite it as x to the -3 before I do my power rule process, before I bring down the exponent down and subtract 1 from the exponent. And last thing is we want to resolve all your parentheses and fractional terms before applying power rule. So if I had x plus 5 quantity squared, I first have to get rid of all the parentheses before I can jump through a power rule, before I can apply a power rule. So if I have x plus 5 quantity squared, I first have to write it as x squared plus 10x plus 25. And all the parentheses are resolved before I can go through my power rule process. Okay. So again, the 3 rules are radicals to rational exponents, no variable in the denominator, and no parentheses in the way. Now, we are going to be able to handle derivatives for parentheses later on for more complicated problems that we can't expand or we can't resolve. But for now, we're going to be able to do a power rule for anything that involves parentheses, but we first have to expand all the way out. Okay, be sure that our expression is in the appropriate form. We have to make sure that all of our conditions are met before we apply power rule. So let's start off with a few here. Y equals x to the 7th. And there's a lot of different notations for derivative, and I'll begin showing you each of them as we go along. So for y, we can call the derivative y prime. And let's apply power rule because every condition is met. No radicals to convert to rationals, no variable in the denominator, and no parentheses. So we're ready to do power rule. X to the 7th becomes, what's the derivative? Yeah, bring down to 7 and then subtract 1 from the current exponent. So 7x to the 6th. So 7x to the 6th is going to do the job of describing how the slope is behaving at any point on this original graph. Okay, part B, cube root of x. We want to do power rule to find the derivative, but first we have to rewrite the function. So cube root of x can be rewritten as what? Good, x to the 1/3. And now that we have x to the 1/3, everything is ready to go. So now let's do g prime. Go through power rule. So 1/3 x to the negative 2/3. Yeah, we subtract 1 from the exponent. So minus 3 over 3 to force that common denominator. So 1/3 minus, let me just show you what we're doing here, minus 3 over 3. So that's negative 2/3. Now I'm going to ask that we resolve negative exponents. So we're going to rewrite g prime as, we're going to put that x to the denominator to force that negative to be a positive exponent. So that x is going to share the same space as that 3. So we'll make it 1 over 3x to the 2/3. Any questions with finding the derivative or resolving the negative exponent? Yeah.
How do we know the x goes in the denominator?
So if you see x to the negative 2/3, this x is currently in the numerator. So if we want to force that exponent to be positive, I got to flip that x to the bottom. So that's going to now be with a 3. You can leave your answer in a rational form, or you can put it back into radical form. Either form is fine. Again, you don't have to rationalize your denominator. I prefer to just leave it in rational form, but if you want to put it in radical form, that's perfectly fine. All right, part C. Y equals 4 over x to the 5th. I want to do power rule, but something is out of place. The x. So how can I rewrite it so that the x is in the right place? Or x to the negative 5. So I have to put that x up here before I do power rule. I can't just say, oh, power rule for x to the 5th is 4 over 5x to the 4th. Okay. Power rule is not going to, it's not designed for the denominator. So we have to bring it up to the top first before we apply power rule. So now y prime is equal to, now we bring the exponent down. So what does that look like to begin with? Negative 20 x to the negative 6. And now we have our derivative. The final cleanup process is to bring or resolve any negative exponent. So the x will come back down to the denominator. The 20 doesn't get impacted, so the negative 20 stays up top. So I'm going to rewrite my derivative as negative 20 over x to the sixth.
Oh, wait.
All right. Any questions so far? Okay, part D. We have 4 separate terms. Now, each term are at various different levels of readiness in terms of ready for power rule. And also, anytime you have these terms separated by plus or minus, think of these as individual problems. You can just apply the appropriate rule for each, and then just put them all together with plus or minus. There are no parentheses getting in the way, so we don't have to resolve any parentheses. Each term is its own individual process. Okay, so these are all independent of each other. However, not all of these are ready for power rule. So what I prefer to do is I'm going to wait until every term is ready for power rule before I do power rule. Because what I don't want to do is I don't want to do power rule for one and clean up for the other. Because if you do that, it's really hard to go back and double check your work because you don't know where you are. I would just rewrite everything until every term is ready for power rule, and then just do power rule all at once, or the derivative rule all at once for each of the terms. Okay, so is 8x to the 2/3 ready for power rule? It is, okay. But I don't want to do anything yet, so I'm just going to copy that term down. Okay. Is 5th root of x ready for power rule? No. So I need to rewrite it. So x to the what? 1/5. Okay. 2 over 3 root x is also not ready. So what needs to be adjusted? So 2 things. First off, the radical needs to be converted to a rational, and the variable has to be moved up to the top. So if I convert it to a rational, it'll become 2 over 3x to the 1/2, right? And if I push it up to the top, it becomes what? X to the negative 1/2. So I'm going to say 2/3 x to the negative 1/2. Now, if you thought of this as 2x to the negative 1/2 over 3, that is fine. But I also want to show you that I think a lot of students find it a lot cleaner if they don't have to stare at a denominator numeric value. So anytime you have a denominator numeric value, you can always just push it out in front as a coefficient, and it just feels a little bit cleaner not having to stare at the denominator numeric value. So I'm going to say 2/3 x to the negative 1/2 instead of 2x to the negative 1/2 over 3. I mean, these are the same things, but I think visually this is just feels less stressful. Plus 0.875. Okay, so now every term is right up to the starting line in terms of being ready for power rule. So now let's apply a power rule for each of the terms. Okay, so what would you do with the first term? Yeah, good. 2/3 times 8. I'll make it 16/3 x to the, what's my new exponent? Yeah, because I'm subtracting 1. Subtracting 1 is the same thing as subtracting 3 over 3 if I want to match common denominators. Okay, next term. Exponent. So 1/5 comes down, and then x to the what? Yeah, because I'm subtracting 1, but I got to force that common denominator, so minus 5 over 5. So 1/5 minus 5 over 5 is negative 4/5. Okay, next. What do I do? Yeah, so negative 1/2 comes down, multiplies with 2/3. So I can make it negative 2/6 or negative 1/3. And I subtract 2 over 2, so negative 3/2. And then this is a constant, right? So what happens to a constant? What's the derivative of a constant?
0.
0, yeah. So think of any constant as just some horizontal line, and that horizontal line's slope is 0. So therefore, the derivative of a constant is 0. You don't have to put a plus 0 here. I just want to show you that we did resolve that 0.875. All right. And now the final thing is we have the derivative. We're just going to do some cleanup. So any negative exponent, I'm going to push them back down to the denominator.
Would the last one be 2/3 or 3 over 2?
Oh, sorry, 3 over 2. Thank you. Yeah, so whenever you flip the exponent down, you're going to keep the same fraction, but just change the sign. Sorry, yeah, it should be positive 3 over 2. Again, you can convert all of these to radicals, but rationals in the denominator is fine. Okay, so today we're just going to practice with power rule. Okay. Okay, next page. Okay, example 2, if f of x equals 1 over x squared, find f prime of 2. So this is asking for the slope of this curve at 2. Whenever you see f prime of a number, just always think about the fact that this is a two-step process. We first have to find f prime of x before we find f prime of 2. Okay, so don't think of it as, oh, I can just do this in one step. You typically want to do it in 2 steps. Find your slope formula first, slope function first, and then worry about the slope. But if I want to find the derivative, I first have to get this in the right place, right? So what's out of place for this function?
X is
So how would I rewrite it? X to the negative what? Negative 2. Just negative 2, yeah. Okay. So we're just flipping that variable to the numerator. These mean the same thing, but this is in a better spot for us to apply power rule. Okay, so now f prime of x, let's find the derivative. What's the derivative going to be?
2x. Negative
Negative 2x. Good. Subtract 1 from the exponent, so it becomes negative 3. Okay, I'm going to clean up, and then I'll find my slope. Now, when I bring the x down to the denominator, the 2 doesn't come along with it because the negative 3 only sees the x. So the x comes down, but the negative 2 stays above. Okay, now I have my slope formula. I can now find the slope at a specific point. So now I'm going to find the steepness of this curve at 2. So f prime of 2, the slope of the tangent line is going to be negative 2 over 8, which is negative 1/4. Okay, example 3. If the function is cube root of x squared, write the tangent line equation of f of x at x equals 1. So we're going to find this order pair from the function. We're going to find the derivative, and from the derivative, we'll find the slope. Once we have our order pair and our slope, we'll write our tangent line equation in point slope form. Right. Let me gather the obvious information first. At the function level, we can find the order pair, find the y value. So let's find the y value here. So f of 1 will be the cube root of 1 squared, which just cleans up to be just y. So cube root of 1 is 1, 1 squared is still 1, so my order pair is just 1, 1. Okay, I want to find the derivative, but before I can find the derivative, I first have to get my term ready for power rule. So I can rewrite cube root of x squared as what? X to the 2/3, yeah, 2/3. Okay, so now we're finding f prime. Go through, now we're ready for power rule, right? All of our conditions are in place. Radicals to rationals, no parentheses, no variable in the denominator. So bring the exponent down, 2/3, x to the what? -1/3. All right, let's clean up, and then we can evaluate and find the slope. So now that I have my derivative, I can work on finding my slope. Plug 1 in for x, so f prime of 1 is equal to 2/3 times 1 to the 1/3. And this will still be what? Yeah, because 1 raised to anything is still what? 1. Still 1. So I'm just left with 2/3. All right, I have everything that I need. I have my point. I have my slope. Now I'll just put it into point slope form. Okay, any questions with 3? All right, example 4. These are the types of problems that are the most complicated in terms of power rule. But I want to add one more thing here. If you can make that denominator a 2√x. So whenever you see like this complicated fraction, but there's only a single term in the denominator, what you want to first do is we want to do power rule for these terms, but we're first going to split into individual fractions first. The advantage of that is if you can split up into individual fractions, then rather than one complicated single expression, we can split this up into 3 smaller problems. And then each problem can be independent of each other. And we just get each term ready for power rule and do power rule 3 times. So think of it, we want to think of this as 3 or multiple smaller problems rather than one connected, complicated looking problem. So let me first start off by splitting up into individual fractions. And as I do that, I'm going to do some cleanup as well. I can convert square root of x to be what? X to the, the cube root of x is x to the 1/3, but the denominator that will be x to the 1/2. Okay, and I'm going to just go ahead and start splitting up into individual fractions, and I'm going to resolve them as I get to, as I'm ready, when I'm ready to work on each of them. So now, if we can clean each of those fractions up, then I'm really just doing power rule 3 times, once for each individual term. But the x's are out of place. So if I'm going to be merging the x's together, guess what I'm going to do with the exponents? What operation am I going to do if I want to merge these x's together? Subtract. Okay, we're not going to divide. We're going to subtract. Okay, so what's 4 minus 1/2? So the same thing as 8/2 minus 1/2, which is 7/2. And then what's 2 minus 1/2? 3/2. And then 1/3 minus 1/2. I do common denominators. That's not either 3 or 2. I have to use 6, right? So 1/3 minus 1/2 is same thing as denominator 6. So 2/6 minus 3/6, which is what? Negative 1/6. So now all this is still part of my cleanup process. I haven't done anything with power rule yet. I haven't brought down the exponent and subtracted 1 from the exponent because we're still in our cleanup stage. Any questions so far? So this is the same thing as this. Okay? We've just rewritten it into a different form, but these are still all equivalent to the function. Okay. Now these are pretty much ready for power rule, but I just want to show you that anytime you have a numeric value stuck in the denominator, you can push those out as a fractional value, so it doesn't seem to be distracting, getting in the way. So a 2 in the denominator is same thing as what in front? 1/2. I think visually it's just cleaner if you don't stare at the number below your variable. And then I can push this out as what? 3/2. And this one is already ready to go. Okay, so now every term is at the starting line. We can now apply power rule, which bring the exponent down and subtract 1 from the exponent. So now f prime, bring the 7/2 down. What's my new exponent? 5/2. Yeah, 7/2 minus 2/2, which is 5/2. Bring the exponent down, multiply with whatever coefficient you see. 9/4 x to the, what's 3/2 minus 1? Yeah, 3/2 minus 2/2. So just 1/2. And then 2 times negative 1/6, negative 2/6, or you can make it 1/3. And then what's my new exponent?
Negative 5/3.
What's negative 1/6 minus 6/6?
Negative
7/6. So we have our derivative. And now clean up. We're just going to, I'm going to reduce that 2/6. You don't have to, but I'm going to reduce it. And I'm going to push that x back down to the denominator because there's a negative exponent sticking out. Okay, this is the most involved that power rule can get. So we'll definitely do more practice with this. But for now, I just want to know, do each of the steps make sense? And if not, I want to be able to kind of answer some questions. All right. Example 5. Find f prime if the function is 3x times x plus 1 quantity squared. We want to do power rule, but what's getting in the way here? Parentheses. Yeah, we got to get rid of all the parentheses before we do power rule. So just be careful with your order of operations. We can't distribute the 3x until the x plus 1 squared is resolved. So let's figure this piece out first, and then we can distribute the 3x through. Okay, distribute the 3x through, add exponents. Now we're ready for power rule. Every term is nicely separated. There's no radicals getting in the way. There's no variable in the denominator. Everything is separated. Now we can do power rule. This should be pretty straightforward. What does 3x cubed become?
X squared.
Okay. What does 6x squared become? 12x, okay. What do you think 3x turns into? 3x becomes just 3. Okay. Think of this as a linear function, right? If I gave you y is equal to 3x plus 4, what would you say the slope of this line is? What's the y equals 3x plus 4? 3, right? And so whatever, if anything is at a degree 1, it'll just turn into a constant. And look, if you go through power rule, every degree falls by 1, right? 3 goes to a 2, 2 goes to a 1, degree 1 drops out. I'm just left with that coefficient. Before we move on, I just want to talk about converting radicals to rationals and some of the trouble spots that students experience. Let me just go through a couple of them here. Square root of x, what's that? X to the 1/2, okay? Because the reason why there's a 1 and 2 there is because you know there's a hidden 1 here and there's a hidden 2 here, right? Okay. What about cube root of x? Okay, x to the 1/3. Okay. What about fifth root of x squared? X to the 2/5. Okay. What about square root of x to the 7th? X to the 7 over 2. Okay, put a star next to this one. This is the one that students have most trouble with. All right. So, every year this is going to happen. I'm just hoping that we can reduce the number of this occurrences. A lot of students want to say, oh, they want to, when they see something is missing, I think a lot of students want to assume that it's a 1 there. So a lot of students want to say x to the 1/7, which is not the case. Or they realize the 2 there, but students tend to read from left to right. So they would also say x to the 2/7, and that's not correct either. This is x to the 7 over 2, not 1/7 or 2/7. So just be aware that this is where a lot of mistakes occur because of the way that we tend to assume or read things. And if you forget what numbers go where, start with this, right? You know square root of x is x to the 1/2, so just figure out where the numbers go. You know there's a 1 here, there's a 2 there, so if there's a missing number to the right, it must be a 1. If there's a missing number in that root spot, that must be a 2. All right. let's go to page 17 and let's see if we can work through some of these problems here. So page 17. Again, sorry if I put page numbers all out of place here. All right, so we're going to apply power rule for every one of these problems, but some of them are ready for power rule, others are not. And we have to make sure that all of our conditions are met. Radicals converted to rationals, denominator variables brought to the top, and all parentheses resolved. So number one, we start off easy. There are no issues. Every term is ready for power rule. So f prime is equal to, okay, walk me through this. 3x to the fifth becomes 4x becomes good. 156, 0. Good. All right, number 2. Are we ready for power rule? No. What needs to move? X is 6. Does the 3 move along with it? No. So keep that in mind as well. Only the x moves, not the 3. If the 3 was going to move with it, it would need a parentheses 3x to the 6th. But here it's only going to be the x. So when you move the x, it becomes 5x to the negative 6 over 3. But what's a way for us to rewrite it so we don't have to stare at that 3 below the x? Make it 5/3. Yeah. 5/3 x to the negative 6. Everything is ready. Now we're ready for power rule. Go ahead and apply power rule. Do some cleanup. Number 3, g of x equals 3 square root of x to the 9th. How will we rewrite this? 3x to the what? 9 over 2. Yeah, 9 over 2. This is the trouble spot here. If students are going to make mistakes with converting radicals to rationals, this is the one that causes the most issues. Okay, everything ready for power rule? Go ahead and apply power rule. G prime. No negative exponents to resolve. Okay, you guys want to try number 4 on your own? Okay, questions with 4? So number 5, we have to expand the parentheses out and move the exponents to the right place. So try number 5. Okay, let's skip to page 18. And let me do another extended fraction one with you so that you'll have something to, we can get some more of that practice in. So page 18, next page. Everybody okay with number 5? Okay, let's try number 11. So we have a fractional expression, but let's force this into 3 separate fractions so that we can just make them 3 individual problems rather than one complicated looking one. And then once we have them separated, we can get each term ready for power rule, and we can apply power rule.
The last one is the negative 1 half.
So I need to push that x up to the top. So it just comes up as x to the negative 1 half.
Oh, okay.
Right.
We didn't like subtract anything.
Well, it's technically 0 minus 1 half. And this one be 1 minus 1 half. This would be 4 minus 1 half. All right, so now every term is ready for power rule. Everything is at the starting line. Now we can do derivative. Mm-hmm.
In the second step, where did the 7/2 come from?
So I have to subtract the exponents to get the variable to come up to the top. So 4 minus 1 half, the same thing as 8/2 minus 1/2. Okay, your homework is just these 2 pages, page 17 and 18 all. You're just practicing with power rule. We'll practice with power rule some more tomorrow. And then we'll also do our, we'll start the next section as well. Maybe we won't have to move.
Yeah.
All right, guys, we're gonna, go down to 2204. This one was here, we'll walk with the guys around.
I hear you, this one more tomorrow, will I get punched up? Because it was then
I like to say, do I think, oh, that's doing that, I don't, it's the other guys, or it's not like
It's fine.
I have it on.
Like every one of the flowers.
Also, I'm gonna.
That's it. What's the?
What? So what time's good? Then here, go to middle school. Jackson, you work this weekend today?
Bro, I would do, the only day I'm gonna work is Monday. Monday was 11.5. Bro, why wouldn't you work on Monday?
When's the late?
You would have made more working Monday than you would have.
That was aimed for Thursday. Yeah, happened to be.
Yeah, so can I do, in the morning on Thursday?
So,
Okay.
so thanks.
Thank you.
Thanks, Danny.